Good morning. I wanted to review these notes real quick to just kind of look at them. So these you already have. You don't need to copy this down again. But remember how we made perfect squares with this? So we're going to talk about perfect squares today still a little bit. And then we're going to talk about perfect cubes. So you have a list over here of perfect cubes already in your notebook. So if you want to look at that, I'm going to do a little drawing here. You can add it to this page or you can add it to the cube page. So this is our perfect cube roots page. We're going to start here. And maybe I'll do that up in the title part just to kind of give you a visual, or maybe at the beginning. Maybe I'll scooch this down. Let's do that. No, let's estimate first. Let's estimate. No, let's do that. Okay. Not quite sure which one would be better first. So let's do our little drawing of what is a cube root, and then we'll get to looking at squares and cube roots and estimating what numbers they would be between. So like with squares, here we'll go with that 3 by 3 first. If we were to draw a perfect square, it would be 3 by 3, which is 9. So 9 can make a perfect square. 9 little unit squares can make a perfect square. And our root of that would be 3. So it would be a perfect square. Square. Right there, a little F cube. For a perfect cube, it's the same idea, but this time we're looking at it in 3 dimensions. Hence why we have a cubed exponent is 3. So if we do cubed roots, it would be a third root. So we're looking at it in a sense of 3s this time. So we're looking at it 3s with 3s. So if we were to make a cube, and I'm going to draw the same thing, but a little bit lower here. If we were to make a cube, now I'd start with my same 3 by 3, just to kind of give you a nice, beautiful little visual there. But that's still a square. If you then connect your line out a little bit diagonally, we're going to start to make it a 3-dimensional cube. Not bad. Decent drawing on my thing there. So if we look at our cube here, we have our front face. And each of those cubes are also 3-dimensional. So we're not looking at the flat surface area. We're kind of looking at volume here. So if we think about it, like this corner cube has, it's like we're making little tiny cubes in this cube. You can kind of see that there. So if we think about it that way, this perfect cube would have how many little cubes inside of it? Well, that's something to think about. Let's go backwards with volume here. We know the volume of a 3-dimensional figure is our length times width times height. We need 3 different dimensions. Cubes have exponents of 3 because we're in 3 dimensions now. So if we have a side length of 3, and this is 3, and this is 3, so we have 3 times 3 times 3. So that would be 3 times 3 times 3, also known as 3 cubed. Lovely. But let's look at what that would be. What is 3 times 3 times 3? Well, 3 times 3 is 9, times 3 is 27. So 3 cubed is 27. If I asked you backwards, if I said, hey, if I have 27 cubes, little cubes, can I make a perfect cube with those cubes? It's a weird question. If that were the question, it'd be the cube root of 27. Well, the cube root of 27, if we had a perfect cube with 27 unit cubes in there, what would our side length be? It would be 3. So that's why if you notice here, we'd have 3 cubed is 27. So then the cube root of 27 is 3. We can go forwards through that, backwards through that. There's our idea on cubes, and I can draw a few more for you in class if you need. So estimating non-perfect squares and cube roots. Estimating. What's nice is this list is going to be very helpful. So we're going to do a few examples here for estimating non-perfect squares. What we're going to do is we're just going to go for the basic level of what 2 numbers would it be between. What 2 numbers would it be between? So let's look at a square first before we get into some cubes, shall we? Because we're much better with these square roots at this point. So if we were estimating, and the keyword is estimating, we're not finding the exact decimal. We're not simplifying, we're estimating. We're giving it, it's about between these two things. So let's look at our first example here. Example 1. Let's say we're going to have a square root of, let's pick the number 30. That sounds good. 30. 30 is a nice number. We could simplify, true. We could find our exact decimal, true. But we're estimating non-perfect squares. We want to say, if we were to put that in the calculator, what two numbers would it be between? Now, my favorite way to do this is looking at this beautiful list here. I guess I could make the little screen larger. Oh, I moved it to the other screen. Whoa, technology. Okay, so all we have to do is look down our list and see where would 30 fit between. Oh, well, it's bigger than 25, but less than 36. So it would be right between these two numbers here. It's going to be between 5 and 6. So that's all we put. We would write, can I write it? Oh, there we go. Between 5 and 6. That's an and sign. Kind of looks like a weird 8. Maybe I'll use the word. I'll just type it. Between 5 and 6. That's all we got to do. So I'll just try another one there. What if we were to do... oh, maybe I'll just scroll down a little bit. Apparently I can't. Okay. Nope, I'm drawing again. So sorry for that interruption. Okay, here we go. Example number 2. Let's try another one. And you know what you could do is you could pause the video, see if you can guess the right answer. Let's go with, we're going to estimate. Let's go with 87. 87. Let's estimate. Did you find the answer? All we got to do is look at our list and find, okay, 87. Oh, look, it's bigger than 81, less than 100. It's going to be between these two, 9 and 10. Yes, this question is that easy. Yes, they are. Between 9 and 10. Lovely. All right, we're going to do 2 more. But they're going to be cubes this time. So if we're going to estimate cube roots, now how we write the cube roots, notice there's no number in there. There's no number in there. That's implying a little square root, a little 2 in there. Invisible numbers. So for this one, we have a little tiny baby 3 sitting in that little pocket. It's like the tiniest 3 you've ever seen. So the tiniest 3 you've ever seen in a little pocket there. Okay, cube root of, let's pick a number. Let's go 30, because that was our first one. So this one's going to be different because it's not a square root, it's a cube root. So we want to see if we had 30 unit cubes, what numbers would those be between? Okay, so we look at our cubes list over here and we see, okay, 1, no, it's bigger than 1, it's bigger than 8, it's bigger than 27, ooh, but it's less than 64, so this one's between 3 and 4. Between 3 and 4. All right, I'm going to do one more. And again, try to pause the video, see if you can guess the answer, which I think you can. My video, well, my face is going to be over there for now. Okay, so if we have our cubed root, that little 3 in the pocket, let's go with our cubed root of, let's go with 500. Let's go 500. 500 here. Pause the video, see if you can find the answer. Okay, now that you found the answer, it should be, well, between 8 and 9. Between 8 and 9. Oop, I forgot the word between. Between. That says between. Okay. Sure it does. Okay. And the next thing I want to show you is how to simplify cubed roots. So we're going to simplify cubed roots for our next part here. Let's see, can I... I'll just write it. simplify cubed roots. So we know how to simplify square roots. We've been practicing that for a while now. This is very, very similar. And we have still the same options of methods. We can do pairs or squares, same idea. But in this case, it's not quite pairs because square roots had 2. So in this one, that's not really pairs. It's groups of 3. All right. So our first one, we're going to call it prime factorization because that's the fancy schmancy name for our method. So our first one is, I can type now, factorization. Then I'm going to type it now, but further down for our notes. Don't write this part yet. Write it when we're done doing our prime factorization because I'm not sure how many lines we're going to need. And then we'll do with perfect cubes. So that'll be our pairs and squares kind of idea. Pairs and then squares. But since we are in cubes, we don't really have pairs anymore. We're going to do groups of 3. So what that looks like is if we were to simplify, it looks like we're on example 5. Okay, if we were to simplify the cubed root of 16 x to the 7th. 16x to the 7th. Just like we do with our pairs, we're going to start making a tree for 16. Okay, 16 can split into 4 times 4. And our trees are looking very good. We got 2 times 2. Oh, those are both prime. And 4 can split again, so we got 2 and 2. There's our prime factorization for our 16. So we have our cubed root. Don't forget that little 3 in the pocket. Notice I'm drawing that line very far away. You want to know why? Look how many x's we're going to draw. 7 of them. Okay, but first we need our 4 2's in there. So let's get our 16 broken down into its prime factorization of 2 times 2 times 2 times 2. Then x to the 7th. We have 1, 2, 3, 4, 5, 6, 7 x's. Now, last time it was a square root, so we can only take out pairs of 2. Since it's a cubed root, we need a group of 3 for those 3 dimensions of our cube, or length, width, and height. So what we're going to circle are groups of 3. We have 3 2's right here because it's a group, and this little 3 kind of tells us right there, that little 3. That was supposed to be an arrow to the 3. It's okay. So that 2 can come out of the radical. This 2 stays. And then we see if we have any other groups. There's a group of 3 x's. Okay, that one's coming out. And another group of 3 x's. That one's coming out. Here we go. Oh, and we have another one left over. So inside of our cubed root, we still have our 2. And this 2 right there, if you want to know where it came from. And then this x here. So those are still in there. And all we have to do is like multiply our coefficient stuff together, multiply our radicand together to make it look pretty at this point. So we have 2 times x, so that would be written as 2x squared on the outside there. And then our cube root of 2 times x would just be written as our cube root of 2x. And we've simplified our perfect cube using kind of like pairs. Our prime factorization is technically what we used. All right, the next one. We're looking at our perfect cubes here. Da-da-da. So this time we're using our perfect cubes method. This is like our perfect squares method, but it's dealing with cubes. So we're going to use this list and find our perfect cube, the largest perfect cube that's in there. So this is just the other method. That way you can see both of them. All right, so we're going to do the same exact one. So we're going to simplify the cubed root of 16x to the 7th power, but we're going to do it with our other method. Good news is we know we're going to get 2x squared times the cubed root of 2x as our answer. We know this. If you want to pause and see if you can try to figure out how to get there with perfect cubes, go for it. But it's kind of a new topic, so we're going to learn here together. So if we split up 16 into its factors, we want a factor that is a perfect cube. So if we look at our cube list, 27 is already too big. It's too big. It's bigger than 16. So we just got to check 8 because 1 doesn't help us. So can 16 divide by 8? Yeah, so 8 is our perfect cube. So we're going to break it down into 8 times 2. And if we're breaking down x to the 7th into cubes, we want to break it down into groups of 3, kind of, but we want to split it up into 3s. So we have an x cubed times an x cubed times an x. Now, let me talk about what we did and why we did it. Remember our product rule for exponents? If we go backwards to get to the 7, 3 plus this secret 1 is 7. So 3 plus 3 is 6 plus 1 is 7. So that's why we wrote it this way. You can put the 1 there if you want. You don't have to. I put it so that we could see it there. So we just broke it up into perfect cubes. X cubed is a perfect cube. The cube and the cube root will cancel out. Lovely. That's what we want. So I'm going to rewrite these broken down. So there's going to be quite a bit of writing here just because these are our notes. And I know parts of this will become mental math for those of you who like this perfect cube method. But since these are our notes, I'm going to break it down for you here. So we're going to have our cubed root of 8, our cubed root times our cubed root of 2, times our cubed root of x cubed, times our cubed root of x cubed, times our cubed root of x to the first power, but I'm just going to write x because it's the same thing. So that's what we have here. And then we're going to find our perfect cubes and simplify those. So if we have here this cubed root of 8, the cubed root of 8, if we have 8 unit cubes, we can make a perfect cube, and that dimension would be 2. 2 times 2 times 2 gives us 8. So our perfect cube of 8 is there. This 2 root 2 is going to stay in the radical, so I'm going to leave that for later. This cubed root of x cubed, those cancel out, so we're left with just x. The cubed root of cubed, those are inverse operations, so we are left with just x, and those are being multiplied. And then as we stated before, this 2 and this x stay in the root cubed, and since we are multiplying, we can put them right back together. See, sometimes people like this part. That's a weird looking too. To do it mental math, so they kind of start from up here and they say, okay, this 2 can't, so it's going to stay in the radical. This x can't, so it's going to stay in the radical. So they immediately just jump down to this step down here. That's fine. Always fine. From here, we just make it look pretty and multiply our coefficients together. 2 times x would be our 2x squared, which we knew the answer to already. And then we had our cubed root of 2x. Bring these lovely notes we are reviewing tomorrow. Getting ready for the test. This is the last of the notes. I mean, not tomorrow. Whatever next class is. Next class. You're right. Next class.